The National Electrical Code, or NEC, mandates that conductor ampacity be adequate for the intended load. In this specific scenario, the load consists of a 50 amp hot tub. Crucially, the NEC also dictates the sizing of the ground conductor relative to the circuit's ampacity. For a 50 amp circuit, the ground conductor must be a minimum of 6 gauge. Consequently, to adhere to NEC regulations, the conductors in this instance must be at least 6 gauge. It is inaccurate to presume that the majority of installations employ Romex cable. While Romex is prevalent in residential wiring, it is not the exclusive cable option. In this situation, using Romex would be unsuitable since the conductors necessitate a 6 gauge size. It is crucial to understand the relationship between conductor size, ampacity, and the applicable electrical codes. The NEC provides tables and guidelines for determining the appropriate conductor size based on the expected current draw of the load. Factors such as the type of insulation, ambient temperature, and the number of conductors in a raceway or cable also influence the ampacity of a conductor. When selecting conductors for a hot tub installation, it is essential to consider all these factors to ensure a safe and compliant installation. Ignoring these requirements can lead to overheating, insulation breakdown, and potentially hazardous situations. Firstly, consider the ampacity. The ampacity of a conductor is its current carrying capacity, expressed in amps. The NEC provides tables that list the ampacity of various conductors based on their size, insulation type, and temperature rating. The ampacity of the conductor must be equal to or greater than the non-continuous load plus 125% of the continuous load. Secondly, consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Thirdly, consider the grounding. The grounding conductor provides a path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electrical shock. The NEC requires that the grounding conductor be sized according to the ampacity of the circuit. For a 50 amp circuit, the grounding conductor must be at least 6 gauge copper. Fourthly, consider the environment. The environment in which the conductors are installed can affect their ampacity. For example, conductors installed in a hot or humid environment may have a lower ampacity than conductors installed in a cool, dry environment. Fifthly, consider the type of equipment. The type of equipment being served by the conductors can also affect the required conductor size. For example, motors and other inductive loads may require larger conductors than resistive loads. Sixthly, consider the distance. The distance the conductors will be running from the power source to the load can impact the conductor size needed due to voltage drop. Longer distances mean more resistance in the wire, leading to voltage drop, and therefore larger wire sizes might be required to compensate. Seventhly, consider the NEC tables. The NEC contains numerous tables providing guidance on proper wire sizing. For example, Table 310.16 lists the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees C through 90 degrees C in free air, based on ambient air temperature. Other tables cover different installation conditions and conductor types. Eighthly, consider local amendments. Be aware that local jurisdictions may have amendments or additions to the NEC. Always check with the local electrical inspector to ensure compliance with all applicable codes and regulations. Ninthly, consider future expansion. Consider the possibility of future expansion or increased load when determining conductor size. It may be prudent to install larger conductors than currently required to accommodate future needs. Tenthly, consider professional advice. If you are unsure about any aspect of conductor sizing, consult with a qualified electrician or electrical engineer. They can assess the specific requirements of your installation and recommend the appropriate conductor size. In summary, proper conductor sizing is critical for electrical safety and performance. Always follow the NEC and other applicable codes and regulations when selecting conductors. Remember to consider ampacity, voltage drop, grounding, environment, equipment type, distance, NEC tables, local amendments, future expansion, and professional advice. Using the correct size conductors is essential for safe and efficient operation of electrical equipment. Undersized conductors can overheat, causing insulation damage, fire hazards, and equipment malfunction. Oversized conductors, while not inherently dangerous, can be more expensive and difficult to install. The NEC provides specific guidelines for sizing conductors based on the application load and installation conditions. Ignoring these guidelines can result in unsafe and non-compliant installations. The role of the ground wire in a 240-volt circuit is to provide a safe path for fault current to return to the source. This allows the overcurrent protection device, such as a circuit breaker, to trip and interrupt the flow of electricity in the event of a fault. Without a properly sized ground wire, fault current may not be able to return to the source quickly enough, which can lead to dangerous voltage on metal parts of equipment and increase the risk of electrical shock. The size of the ground wire is determined by the size of the circuit conductors. The NEC specifies the minimum size of the ground wire based on the ampacity of the overcurrent protection device. For a 50 amp circuit, the NEC requires a minimum of 6 gauge copper ground wire. It is important to note that the ground wire must be properly connected to the equipment grounding system to be effective. This includes bonding all metal parts of the equipment together and connecting them to a grounding electrode, such as a ground rod or water pipe. The purpose of bonding is to create a low impedance path for fault current to flow back to the source. A low impedance path helps to ensure that the overcurrent protection device will trip quickly in the event of a fault. Improperly sized or installed ground wires can compromise the safety of an electrical system and increase the risk of electrical shock. It is always best to consult with a qualified electrician to ensure that the grounding system is properly installed and meets all applicable codes and regulations. Remember that electrical codes are in place to protect people and property from electrical hazards. Following these codes is not only the law, but also a matter of safety. The NEC is updated every 3 years to reflect changes in technology and best practices. Staying up to date on the latest code requirements is essential for anyone working with electricity. In addition to the NEC, there may be local codes and regulations that apply to electrical installations. It is important to check with the local electrical inspector to ensure compliance with all applicable codes. Electrical work should only be performed by qualified individuals who have the necessary training and experience. Working with electricity can be dangerous, and it is important to take all necessary precautions to avoid electrical shock and other hazards. Always disconnect power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. If you are unsure about any aspect of electrical work, consult with a qualified electrician. Remember that electrical safety is everyone's responsibility. By following safe work practices and adhering to electrical codes, we can all help to prevent electrical accidents. In addition to the 6 gauge requirement for the ground, be sure to check the NEC for any specific requirements related to ground fault circuit interrupter, or GFCI, protection for hot tubs. GFCI protection is often required to protect against electrical shock hazards. A GFCI is a device that monitors the current flowing in a circuit and trips the circuit if it detects a difference between the outgoing and returning current. This difference indicates that current is leaking to ground, which could be a sign of an electrical fault. GFCIs are typically installed in areas where there is a risk of water contact, such as bathrooms, kitchens, and outdoor locations. Hot tubs are considered to be a high-risk area for electrical shock, so GFCI protection is typically required. The NEC specifies the requirements for GFCI protection in Article 680, which covers swimming pools, fountains, and similar installations. Be sure to consult Article 680 for the specific requirements related to hot tubs. In addition to GFCI protection, other safety measures should be taken when installing a hot tub. These include proper bonding of all metal parts of the hot tub to the grounding system, using listed and labeled equipment, and following the manufacturer's instructions for installation. Hot tubs should be installed by qualified electricians who are familiar with the NEC and local codes. Improperly installed hot tubs can be a safety hazard and can lead to electrical shock or other injuries. It is important to take all necessary precautions to ensure that a hot tub is installed safely and correctly. Consider also the type of conduit being used. Electrical metallic tubing or EMT is a common choice, but other options like rigid metal conduit or RMC or even PVC conduit may be suitable depending on the installation environment and local codes. Ensure the chosen conduit is appropriately sized to accommodate the conductors and any required bonding conductors, allowing for easy pull-in of the wires without damaging the insulation. The NEC provides tables for conduit fill, specifying the maximum number of conductors allowed in a given size of conduit. When pulling the conductors, use a pulling lubricant to reduce friction and prevent damage to the insulation. Avoid sharp bends in the conduit, as these can make it difficult to pull the wires and can also damage the insulation. After the wires have been pulled, be sure to properly terminate them at both ends, using appropriate connectors and ensuring a tight and secure connection. Double-check all connections to ensure that they are properly made and that there are no loose wires or exposed conductors. Finally, before energizing the circuit, test the installation to ensure that it is working properly and that there are no ground faults or other electrical hazards. Use a multimeter to check the voltage and current and to verify that the grounding system is properly connected. If any problems are found, correct them before energizing the circuit. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before performing any electrical work. Remember that electrical work can be dangerous, and it is important to take all necessary precautions to avoid electrical shock and other hazards. The original question mentions a 50 amp GFCI breaker. Confirm that the breaker is properly rated for the load and that it is functioning correctly. Test the breaker regularly to ensure that it will trip in the event of a ground fault. If the breaker is not functioning properly, replace it immediately. Ground fault protection is essential for hot tubs as it can help to prevent electrical shock hazards. Make sure that the GFCI breaker is properly installed and that it is working correctly. In addition to the breaker, the hot tub itself should also be equipped with a GFCI device. This device will provide additional protection against electrical shock. Test the GFCI device regularly to ensure that it is functioning properly. If the device is not functioning properly, replace it immediately. Hot tubs should be inspected regularly by a qualified electrician to ensure that they are safe and that they meet all applicable codes and regulations. The inspection should include a check of the wiring, the grounding system, the GFCI protection, and all other electrical components. Any problems that are found should be corrected immediately. Proper maintenance and inspection of hot tubs are essential for ensuring their safety and preventing electrical accidents. Finally, always follow the manufacturer's instructions for the operation and maintenance of the hot tub. This will help to ensure that the hot tub is operating safely and efficiently and that it will last for many years to come. The manufacturer's instructions will provide guidance on topics such as water chemistry, filter cleaning, and cover maintenance. Following these instructions will help to keep the hot tub in good condition and to prevent problems from developing. The overall condition of the hot tub itself is also very important for the safety of the installation. Check for any damage to the hot tub shell, the plumbing, or the electrical components. Repair any damage immediately. Do not use a hot tub that is damaged or that is not functioning properly. A damaged hot tub can be a safety hazard and can lead to electrical shock or other injuries. It is important to take all necessary precautions to ensure that a hot tub is safe to use. This includes following all applicable codes and regulations, using qualified electricians, and performing regular maintenance and inspections. Remember that electrical safety is everyone's responsibility. By following safe work practices and adhering to electrical codes, we can all help to prevent electrical accidents. Review the local requirements and guidelines in New Hampshire to ensure full compliance, as regulations may vary slightly from the National Electrical Code.